Please go ahead.
Okay, so welcome back, everyone, for the second lecture on dark matter. And take it away, Katelin.
Great. Okay, let me share my screen again. Okay, so yeah, thanks everybody for coming back to lecture 2 on dark matter. Again, it's a real pleasure to be giving these lectures. As I was mentioning, it's currently again 6 a.m. in Montreal, and it's minus 30 degrees Celsius if you include the wind chill factor. So, you know, it's a cold one, but yeah, definitely glad to have something to distract me on this cold day. So just a quick recap from some of the things we talked about last time. So we had an hour and a half last time where we talked about potentially a dizzying array of different cosmological and astrophysical probes of the properties of dark matter, the existence and the properties of dark matter. I certainly don't remember, I don't expect you all to remember all of those different probes at any great level of detail because we went so quickly. As I said last time, this is an incredibly broad field, so it's very difficult to do justice to the real breadth of work people are doing in this area. I'm trying my best, but certainly don't expect you all to have perfect recall. So I really just wanted to briefly make sure again that we're on the same page and recap some of the requirements that we're going to put on any theory of dark matter. These are requirements that basically are going to make sure that we're meeting all of the observational criteria that are going to match between our theory and our observation. Okay, so the best measured property of dark matter is its abundance. We know it has to be around 25% of the critical density. The number is really 26.8. I mean, it's known at the sub% level, okay, but it's roughly 25% of the critical density of the universe. This comes in from primarily early universe measurements. For example, we know the baryon density and the total matter density separately, and we know that they're not the same. We also see the unique effects of collisionless dark matter in the CMB and in clustering. Okay, so that's how we're able to tell that dark matter has to be roughly 5 times as abundant as regular matter, as baryons. Okay. We saw that by looking at early universe probes like Big Bang nucleosynthesis, we know that the dark matter can't be thermal and relativistic around that epoch. Okay, otherwise it's going to spoil and effective. It's going to spoil the Hubble expansion rate during that epoch, which is a very important input to determining when various nuclear reactions freeze out. We also know that the dark matter, whatever it's doing in the early universe, it has to be pretty boring by a redshift of roughly 10 to the 7. In other words, it can't do anything like free stream during these epochs. Otherwise, structure is going to get erased on small scales. It also can't interact too much. And similarly, structure can get erased in that case. We also saw the example, possibly one of the most famous examples of pieces of evidence for dark matter, which is merging clusters. We see evidence in these systems for a component of matter that looks collisionless. Okay, so we know both from these merging clusters as well as from clustering, which is a probe of the early universe, we know that the dark matter is not interacting very much, either with itself or with particles in the standard model, baryons in the plasma. Finally, we saw that dark matter has to have a very long lifetime because, as we saw, it was born in the early universe. Okay, so we know what omega dark matter is from early universe probes, but we still see the effects of omega dark matter equals 25% at redshift 0 at the present day. So whatever this dark matter is, if its decay lifetime, if it has some decay lifetime, it has to be longer than the age of the universe. Okay. So these were the sort of observational requirements. We also saw that if we focused in on one theory of dark matter, then the mass of whatever the constituents of dark matter are, that's quite constrained. Okay, so just as a quick recap, on this plot, on the very, very high mass end, we basically, have, it's kind of a silly constraint, honestly. It's saying that the smallest dark matter dominated objects that we see can't be some fractional dark matter constituent or particle. That wouldn't make sense. That gives us a bound of roughly 10 to the 5 or 10 to the 6 solar masses. And then on the low mass end, depending on whether the particle is a boson or a fermion, we have different constraints. Okay, so if the particle is a boson, then you get to go down all the way to 10 to the minus 21 eV. At that point, the wave-like nature of dark matter would wash out structure below a certain scale, just because you're not able to localize waves past a certain point. You can recast that in terms of the uncertainty principle. Okay, so below a certain point, below a certain mass, you're going to start erasing small scale structure. The fact that we see small scale structure means that dark matter can't be lighter than that if it's 100% of the dark matter. As a caveat, if you start playing with fractional components of dark matter, this bound is significantly relaxed. Okay, so that's the case if dark matter is a boson. If dark matter is a fermion, we have a slightly different constraint, again, coming from quantum behavior. In very low mass dark matter halos, we have this Tremaine gun bound, which says that because of the Pauli exclusion principle, you have to ensure that you're able to pack a sufficient amount of dark matter into the phase space that you want. So these very low mass dark matter halos, mass of roughly 10 to the 9 solar masses, localized sort of within a kiloparsec box, and with a typical velocity dispersion of around 10 kilometers per second. So that gives you basically a finite phase space box to cram this dark matter into. So you have to make sure that it's heavy enough that you're not trying to cram too many particles in there to match the observed halo mass. Okay. So, depending on whether it's a boson or not, we have 90 orders of magnitude in mass here to play with a lot of different qualitative behavior. Okay, and we talked about this at the end of yesterday's lecture. This can seem very, very daunting. There's a bunch of different approaches that you can follow. You can, just be very sad and say, okay, 90 orders of magnitude, I'm never gonna make progress here. I don't think that's the right attitude, but who am I to tell you how to approach this? Okay, so I don't think that's a good way to go. But another option is you could just be very phenomenological. So just throw a bunch of data at this problem without really thinking too hard about exactly what are the theoretical constructs for describing this dark matter. That's a valid approach if you have a lot of data. You could try to dovetail the theory of dark matter with other either problems in the standard model or anomalies that we observe. So that's kind of like ambulance chasing, or trying to do things like solve, for example, the hierarchy problem. You can try to make those either observational or theoretical issues part of your theory of dark matter and kill multiple birds with one stone. That's an option. And so and then the final option is to really just focus on explaining the things that we do know, especially the cosmological abundance, given that that's the best measured property of dark matter that we know, given the precision measurements that we have available to us from early universe observables. Okay, so that's the kind of approach that we're going to focus on today. Okay, so I'm actually going to switch now to the iPad. Are there any questions at this point about what I've recapped so far? Because I want to make sure we're all on the same page. Okay. So while I'm sharing screen, just let me know if you have any questions.
Students, are there any questions? Either raise your hand or leave a message in the chat. Katelin, there is none as of now.
Okay, good. No, that's good. I mean, this was a recap, so that means everything was clear. So that's great. So we can move ahead. All right. So as I mentioned, so the focus of today, is we're going to be explaining the dark matter abundance. And the way that we're going to do that is we're going to be using thermal physics. And we're going to do that in the expanding universe at early times. Okay, so this is a little bit inspired by, the approach that you may have seen taken with Big Bang nucleosynthesis, for example, treating all these various nuclear reaction rates in a thermal context. Okay, so that's kind of what we're going to be doing here today. Okay, so let's suppose dark matter has a number changing process. And for the moment, I'm not going to specify exactly what that process is. I'm just going to, for the time being, speculate that maybe it's it involves two dark matter particles. So maybe it's something like an annihilation. We'll revisit that assumption later, but let me just assume that for now. So suppose it's dark matter goes to X, where X is in the standard model, Okay. So first of all, so if we switch off interactions, so if there are no interactions, then the number density of particles is going to just scale with the expansion of the universe. Okay, so the co-moving number density is going to be constant, or equivalently, the total number of dark matter particles is going to be constant. So I'm going to have n dark matter times a cubed is a constant. Okay, and so that implies that if I take a time derivative, so d by dt of na cubed has to be 0. Okay, so if I then use the product rule, right? Then I find that a cubed dn dt plus 3a squared n dA dt is equal to 0. So if I just divide both sides by a cubed, I find n dot plus 3hn is equal to 0. Okay, so that's my baseline behavior for dark matter if there's no interactions. But when we turn on interactions, we have to account for the production and depletion of dark matter. That just goes beyond this sort of baseline red shifting of matter, okay? So we have to account, so now let's account for production and depletion. Okay, so the way that we're gonna do that is just using standard techniques in particle physics. I'll just recap very briefly. So suppose we have some target, okay, and we have some flux of particles in some column. So I have my particles here in this column. The column has cross-sectional area A, and there's a number density of particles n. And I want to know how many particles hit my target. Okay. So first of all, we know that, oh, and sorry, very crucial piece of information. This whole thing is moving at a velocity v. Okay. If everything was stationary, then these particles are just sitting there. They never hit my target. Okay, so they have to be moving with some velocity v. Now, to figure out how many particles hit my target, first of all, I want to know the flux. So how many particles are coming near my target as a function of time? Just how many darts am I throwing at my target? So the flux is basically n times v, right, which is a number divided by an area times a time. So this is a number flux. And so to get a rate of hits, I need to multiply that by an area to get something with dimensions of 1 over time. And the area that I'm going to multiply by is the cross section. So I multiply by sigma, the cross section, Okay, so my rate is n sigma v. So in general, sigma as a function of v is not a constant. Okay, so suppose my particles over here aren't all going with the same coherent velocity. Suppose they have a spread of different velocities, which is the case in any sort of thermal situation, like in the early universe. It's not going to be like, you know, a perfect experiment like that you design where you're shooting particles with a known velocity. There's going to be some random spread. Okay, so to account for the fact that the velocities aren't constant, and in general, sigma as a function of v is not a constant, we have to do a thermal averaging. Okay, so sigma depends on the particle physics, and we need to do a thermal average. So to do that thermal average, we basically just say, okay, well, now I'm going to say my rate that's thermally averaged I'm going to call that gamma, and I'm going to give it these little, brackets here to denote a thermal average. That's going to be equal to the number density of particles, which is not a thermally averaged quantity. You don't have to average it over velocities. It just is what it is. And then I'm going to multiply that times the thermal average of sigma v. Okay. So what I'm basically doing is I'm just, taking sigma v, I'm sticking it in some integral over the velocities, and I'm going to appropriately weight that integral by the basically probability for a particle to have a certain velocity. Okay. So good. So I have my thermally averaged cross section, which accounts for having a spread in different velocities of these incoming particles. Now with dark matter, though, it's a little different because it's not like this idealized case. So with dark matter, we don't have one target. Right, so this idealized case is too idealized. Instead, we have a density of targets. Okay, so instead of what I drew above, the picture looks more like this. I've got my two columns of particles that are moving in these directions, okay, where they both have number density n. So this is going to scale as n squared. So whatever's going on has to scale like n squared, okay? So let me just try this. So let me take my equation from up here that I previously derived for basically having no interaction. And let me just try to stick in a term that seems like it could be appropriate. So I've got my n dot plus 3hn, and that would be 0 if there were no interactions. But now let me introduce a term here. Let me put in a minus n squared sigma v. Okay, so I had said that n sigma v is a rate. So n sigma v has units of 1 over time. The left-hand side over here has units of 1 over time, but times a number density. Okay, so n sigma v times a number density, in other words, n squared sigma v, has the right units. Okay, so this has the right units. Okay, and this minus sign here, I'm going to say is going to account for depletion of dark matter by this dark matter goes to X kind of process that I postulated at the beginning. Okay. I'm also going to introduce a term that can account for the reverse process. So I'm going to put in some term. I'm going to call that have some coefficient X times sigma v. I'm going to assume this is a process which is time reversible in the sense that the cross section to go in either direction is the same. Okay, so this is going to be a term that is independent of n of the dark matter, because this is the reverse process, so there's no dark matter in the initial state, so it can't necessarily depend on the density of dark matter explicitly. So this is independent of n dark matter, and this term accounts for production.
Katelin, there is a hand raised. Maybe we can.
Okay, good. Who has a question?
Yeah, go ahead, Sion. Please ask your unmute and ask.
So for doing the average, so the velocity, does the velocity have some allowed range or something, like for doing the integral?
Yeah, good question. So in the most easiest cases to deal with, you are just averaging over the appropriate thermal distribution for whatever the appropriate statistics are of the particle. So for example, if dark matter in this case is a fermion, you would average over the Fermi-Dirac distribution with a given temperature. So given the temperature, you would know then the distribution of speeds of the dark matter particles. That's for thermal dark matter candidates. Those are the simplest ones. We'll see later on in this lecture that that's not always true. Like dark matter doesn't always have to be thermal. So that would complicate the matter. You would have to then know details about the detailed phase space distribution, which is in general kind of hard to figure out. Does that answer your question?
Sion, unmute and speak. You muted yourself.
Yeah. Thank you.
Great.
Thank you.
Thanks for the question. Okay, so this was my ansatz for what I thought the equation governing these interactions should be. Okay, so now I'm going to basically try to figure out what is this x. So this is an unknown quantity. So I'm going to try to figure out what that is now using some arguments about thermodynamics. Okay, so this is called the principle of detailed balance. And it's this principle that in equilibrium, and maybe I should be more specific, in chemical equilibrium.
Katelin, something seems frozen. We are not seeing anything moving.
Right.
Now,
really? Can you see my cursor?
Yes. Now everything got filled, whatever you said.
Yeah, everything was fine on my side.
Okay. I don't know what happened, but I hope it's good now. Okay.
It's good now. Yeah.
Great. Okay, so in detailed balance, so in equilibrium, and I'm going to specify chemical equilibrium. So what I mean by that is equilibrium of number changing processes. In chemical equilibrium, depletion and production should cancel. So there should be no net change to the number of dark matter particles and dark matter. Okay. And the nice thing about these arguments with detailed balance is you don't have to know the microphysical, like, I made 3 particles over here, so now I had better get rid of 3 particles over there. You don't have to know about any of the details to invoke detailed balance. You just need to basically talk about broad thermodynamic quantities that are broadly averaged. Okay, so if we invoke this argument, then we know that sigma v times x minus n squared has to equal 0 in equilibrium. Okay, so that implies that x has to equal n equilibrium squared. Okay, so even though in producing this dark matter over here, there's no dark matter in the initial state. Okay, so we said that it can't explicitly depend on the number density of dark matter particles because there's none in the initial state to produce dark matter. However, by the principle of detailed balance, we know that whatever is happening with the initial state in the standard model sector, it has to give you this result from detailed balance, such that there has to be some conspiracy so that this X has to be the number density of dark matter squared in equilibrium. So for an equilibrium distribution. Okay, so that leads me to my equation. So thus, the number density of dark matter is governed by this equation, n dot plus 3hn equals minus sigma v times n squared minus n equilibrium squared. Okay, I'm going to highlight this equation because that's an important one. Okay, sometimes this is called the Boltzmann equation. But I actually don't like to call it that because it's not the only Boltzmann equation. It's actually the first moment of the sort of Boltzmann hierarchy. So we actually derived this just now using more intuitive arguments, just for the purposes of this lecture. But if you really want to dig into this a little bit more deeply, one reference that I recommend, which I keep sitting here on my desk at all times, I swear I didn't plan this, I just have it on my desk at all times. You can open up Kolb-Turner and look in more detail at how you derive this equation over here. It comes from looking at more detailed considerations of a full phase space distribution and how it evolves, and then just looking at the 0th moment. But in principle, you can take the first moment, second moment. This is an entire tower of different equations governing the phase space. Okay, but this is sort of the most important one in general, just because, as I mentioned, we care about getting the number density of dark matter correct. That's the best measured quantity that we know. So this is why sometimes people call it the Boltzmann equation, even though there are many of these equations. Okay, so that's the Boltzmann equation. It's very important. It also has the form, so for any math aficionados out there, this is a Riccati equation. So I guess back in the 1800s, when guys were just naming differential equations after themselves, Riccati named this one after himself. So this is a very well-studied differential equation. In general, it doesn't have a closed form solution. Okay, so we can't actually solve for this in closed form, but we can try to figure out some heuristic behavior of this equation in different limits. Okay, so that's what we're going to do now. So to do that, first of all, I want to maybe unpack what's sitting inside of this n equilibrium over here. So if dark matter is produced symmetrically, by which I mean that the chemical potential is equal to 0, then that implies that n equilibrium has one of the two following behaviors. Okay, I'm going to write this is twiddle. I'm doing twiddle physics here. So I'm going to be drawing these little twiddles. That just means it's scales like, or it's proportional to. I'm not going to bother with factors of pi and so on. Okay, so this is either equal or scaling like mt to the 3/2 e to the minus m over t. And that's in the case where the dark matter mass is much, much bigger than the temperature. So it's non-relativistic. Or alternatively, it's going to scale like t cubed. And that's in the case that, dark matter is much, much less than temperature. So it's relativistic. Okay. So that's just an assumption I'm going to make for the time being. So note that there are many variations on dark matter production that violate this. Production okay, but we're just going to assume this now for simplicity, just to get some heuristic understanding. Okay, so given that, there are sort of two regimes for Boltzmann equation. One of those regimes is where n sigma v is much, much less than Hubble. And in that case, the expansion dominates. Okay, so what I mean by that is that dark matter particles have a hard time finding each other. As the universe expands. Okay, so because this is a process where you need two dark matter particles to come in and interact and do something, if the universe is expanding too quickly, those particles are not going to be able to do that. They're not going to be able to find each other. So the expansion is going to dominate the behavior rather than the interactions. The interactions are not really playing a role here. So in that regime, then we have n of the dark matter has to scale like 1 over a cubed. Okay, that's simple enough. We already did that. We already showed that in the beginning. The second regime is when n sigma v is much, much greater than Hubble, as you may have predicted. There's these two cases. And in that case, then n is going to follow an equilibrium distribution. Okay, basically, if you look back at this differential equation, any deviation on the right-hand side of n away from an equilibrium distribution is going to basically increase the rate at which you have a net change to the number density of dark matter. And it's going to do that in a way that drives you towards equilibrium, right? So it wants to go towards equilibrium. If you perturb away, it goes back towards it. It's a stable equilibrium. Okay. In this case, the interpretation is just that dark matter is interacting a lot. And it doesn't care about expansion. So it maintains a distribution that's thermal. Okay, maintains equilibrium. So those are the two regimes that are relevant. As you might have expected, we have these two regimes. One of them is when the inequality goes one way. The other one is when the inequality goes the other way. The crossover point is when those two quantities are equal. So crossover between 1 and 2 occurs when H is equal to n sigma v. Okay, and we call that freeze out. That's freeze out. Okay, and that's only what's happening if the dark matter was in equilibrium to begin with. Okay, so in order to transition from this, oh,
you have a question?
Yes, please go ahead, ask the question.
Yeah, unmute and ask the question.
Hi. So in the first case, there will never, I mean, it will try to reach thermal equilibrium, but it won't be able to reach. Is that the idea? In the first case, where the cross section, where the thermally average cross section is much smaller than Hubble. Correct.
If I look back at this equation, then if I just look at n dot, if I move this 3hn over to the right-hand side, then I have, this term that's scaling like sigma v, and I have this term scaling like, h. So this term on the right-hand side would then dominate the behavior. So this term over here would then be inconsequential in that regime. Mm-hmm.
So you'll always be out of equilibrium for this case.
Yeah, actually, that's really relevant to the point I was actually just kind of making, which is that in order to have freeze out, you have to have started in equilibrium, right? You can't transition from this region to this region unless you were in equilibrium at some point. If you were never in equilibrium, then it doesn't really make sense to talk about freeze out. And so if you're never in equilibrium and this rate is never high, then you're never going to be in the regime where you are driven to equilibrium.
Okay, thank you.
Yeah, maybe let me put that in another, let me phrase that another way. In order to be in equilibrium, you have to have a sufficiently large sigma v such that you are in this regime at some point. So if sigma v is not sufficiently large, then you will not be in equilibrium. Okay. Good. So if the dark matter was in equilibrium to begin with, then it can freeze out. So freeze out. And this is going to be at a temperature that I'm going to call TF, T freeze out. Okay. So after freeze out, we're in case one again. This is in case one, right? So we were thermal, and then we basically had this process drop out of equilibrium. So we're now in case one, which means that after freeze out, the number density scales like the number density at freeze out times A of freeze out cubed over A cubed, right? Because the number density is scaling like A cubed in regime one. Okay, but this is also going to scale like the number density that's an equilibrium number density at freeze out, right? Because just prior to freeze out, we know that the number density of dark matter was following an equilibrium distribution because we were in regime two over here. So it follows an equilibrium distribution. So that was happening just prior to freeze out. We can also relate the scale factors to factors of the temperature. T, so it's T cubed over T freeze out cubed, where here I'm ignoring changes to G star. So I'm ignoring the fact that, for example, like in the standard model plasma, when E plus E minus pairs leave the bath and they heat up the photons and not the neutrinos, that would cause a deviation from this sort of adiabatic behavior. I'm just ignoring that for the time being. I'm going to treat that as just a small correction. Okay. So, so N is going to have this scaling after freeze out. And so now this is the behavior of the differential equation, but there's also two regimes to consider, two physical regimes of parameter space. Okay, so two regimes of parameter space. Is there a hand? Sorry, I thought I saw a hand. Or, no.
That's the old one.
Okay. Okay, so in case A, that's going to be a case where this freeze out temperature is much, much bigger than the mass of my dark matter particle. Okay, so then that means that the number density at freeze out, that's an equilibrium number density, that's going to scale like T freeze out cubed, because, right, if my freeze out temperature is much, much bigger than the mass of my dark matter particle, then the dark matter particle is relativistic when it's freezing out. So if I scroll back up over here to this equilibrium number density, it's going to follow this T cubed behavior. Okay, so this number density at freeze out in equilibrium is going to scale like T freeze out cubed. That means that when I sort of plug this freeze out equilibrium scaling into this equation up here, this equation up here is general. So I just take this and I plug it in here. Then what I find is that N scales like T cubed after freeze out. And this is just like neutrinos. Okay, so this is exactly the behavior that neutrinos have. So if we're in this situation, if T of the dark matter is similar to the temperature of the photons or / the CMB, which is redshifting with time, if that's the case, then we can try to estimate what the mass of the dark matter would have to be. We can estimate based on based on eta, which we saw yesterday is the number density of baryons divided by the number density of gammas. We also know that if the dark matter temperature and the CMB, or the gamma temperature, the temperature of photons, is similar, this is also NB over N dark matter, right? Because these are both relativistic particles. The photons and the dark matter are both relativistic particles down here. So they both have the same sort of temperature scaling. And if they have the same temperature, then that means that up to some order unity factor, accounting for bosons versus fermions or degrees of freedom, these two densities have to be roughly the same. Okay, and we saw yesterday that this number, sorry, let me, squish this a little bit so I have room. Okay. We saw yesterday that this number is around 10 to the minus 10. It's more like 6 times 10 to the minus 10, or actually, sorry, let me round that up, 10 to the minus 9. So 6 times 10 to the minus 10, so let me call it 10 to the minus 9. Okay, so we can estimate the mass of dark matter. So the way we're going to do that is then using the fact that we also know that omega dark matter is roughly 5 times omega baryons. So in the present day universe, where this statement, well, I guess the statement is true at all times, but in the present day universe, we know that the density or the mass density or energy density scales like the number density of dark matter times the mass of dark matter. So if I say that that has to be roughly equal to 5 times the number density of baryons times the mass of baryons, then given, if I plug in this value of eta over here, then that sort of tells me that the mass of dark matter has to be roughly 10 to the minus 8 times the mass of baryons. Okay, I'm doing some rounding over here. I'm not really paying attention to factors of 2 and things like that. I'm just trying to get an order of magnitude level estimate. Okay, so the predominant component of baryonic matter in our universe is protons. Protons have a mass of roughly 1 GeV or so. So this is going to be roughly 10 eV. Okay, so basically what that means is that if we have massive dark matter being bigger than this number that we just estimated, 10 eV, then, and if it decoupled while relativistic, then with T dark matter being proportional to T CMB, we find that if the mass is too heavy, we're going to make too much dark matter. Okay, just based off of this kind of proportionality over here, if we raise the dark matter mass past this estimate, we're going to make too much dark matter. Okay, and that's a problem again, because the quantity of dark matter is like the best measured property that we know about the dark matter. So that's a big problem. So, okay, then that says that the dark matter mass had better be less than 10 eV or so to make right amount of dark matter. But then we're going to run into another problem, because the point at which the dark matter becomes non-relativistic is going to be when the temperature of the dark matter is roughly equal to its mass. And since the temperature of the dark matter is equal to the temperature of the CMB in this case, then the dark matter becomes non-relativistic at TCMB of 10 eV. Okay, but 10 eV is very, very close to the binding energy of atomic hydrogen, right? So a temperature of 10 eV is pretty close in time to when recombination is occurring. Okay, it turns out that recombination happens at a lower temperature. Again, this relates back to what we talked about yesterday. The fact that eta is such a small number means there's a lot of photons on the high energy tail of the distribution. to keep things ionized even once the temperature drops below 13.6 eV. So the dark matter is becoming non-relativistic at this epoch. This is like pretty close to when recombination occurs. So this is close to recombination. Okay, and so as we talked about yesterday, this is very, 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 very ruled out by structure formation. Because as we said yesterday, the dark matter has to basically be behaving like boring, cold collisionless, non-relativistic dark matter by at the latest redshift 10 to the 7. So that's not being satisfied in this case. So this is not a good dark matter candidate for this reason. So if we're in this regime where the freeze out temperature is much bigger than the dark matter mass, that's either going to overclose the universe if the dark matter mass is heavy, or if the dark matter mass is light, we're going to erase structure. Okay. And the one assumption that we made that was perhaps too strong is we assumed that the dark matter temperature was similar to the CMB temperature or to the photon temperature. So what if T dark matter is not equal to TCMB? And that's related to what we talked about a little bit yesterday. So I'm going to leave it as an exercise for anyone who wants to get a better handle on this. I'm going to leave it as an exercise to show that the density of dark matter in this case is equal to m over 94 eV times 4/11 times T dark matter over T gamma cubed. Okay, so that's an exercise if you're interested to delve into this a little bit more. This scenario is called warm dark matter. And we talked a little bit about it yesterday. The current constraints are that M dark matter has to be less or bigger than roughly around 5 keV. So that implies that the G star that you need in the early universe has to be around 5,000. So again, I'm going to leave you to show this as an exercise if you're interested. And this is a problem because the standard model only has around 10 to the 2 degrees of freedom. Okay, so that's also not such a good theory of dark matter. Okay, so in order to make these temperatures as different as they need to be to not be ruled out, you then run into this issue where you need too many degrees of freedom. It's not explained. Where are you going to get the other 10 to the 4 degrees of freedom? So not the most economical theory of dark matter. Okay, so for that reason, I think this regime A, is not necessarily the best place to look for a well-motivated and sensible theory of dark matter. Okay, so that leaves us with regime B, which is when the freeze-out temperature is much, much less than the dark matter mass. So that's freeze-out while non-relativistic. And in that case, then you basically go through these two regimes where you start in an equilibrium distribution. This is regime 2 that we talked about up here. You freeze out, and then you have this scaling later on. So let me draw what the solution looks like for that, just very heuristically. So if I draw n times a cubed on the y-axis, then at very early times, then my equilibrium distribution, which I'm going to draw as a dashed line, this is my equilibrium line, it's roughly constant. Basically, when the dark matter is relativistic at early times, then its number density is going to scale like t cubed, which we wrote above. But at some point, the dark matter becomes non-relativistic. Okay, so its equilibrium number density is being Boltzmann suppressed. Okay, so this is the Boltzmann suppression. By the way, this axis is time. You could also write it in terms of the dark matter mass over the temperature. Okay, so it's being Boltzmann suppressed like e to the minus mass over t. This is not the neatest writing. I apologize for that. We can try to move it. Oops. All right, I'm just going to erase this because I think it's kind of confusing. Okay. Okay, so that's the equilibrium behavior. So we know that at early times, the dark matter is following this behavior. It's going to start doing this. Okay. By the way, this transition to when you start being Boltzmann suppressed is when this is equal to 1 in these funny units over here of dark matter mass over temperature. Okay, but at some point you're going to freeze out. Okay, and we know that after freeze out, at very late times, this has to be constant again, because as we saw up here, this is basically regime 1. So after you freeze out, your number density again scales like 1 over a cubed. So in these units on the y-axis where I'm multiplying n times a cubed, that has to be a constant at late times. So whatever happens, these two behaviors have to be connected to each other in some smooth way between these two regions. So it's going to end up looking something like that. Okay. And this time, by the way, when this happens, this freeze out time roughly corresponds to basically 20, whoops. In these, again, these funny units of dark matter mass over temperature, this has to be 20 in order to give us the amount of dark matter that we see in the final state. That's the relic amount of dark matter. Okay, and this amount of dark matter that we end up with depends a lot on the properties of the particle physics. So if I had made my sigma v, my interactions, weaker or stronger, I would have changed the amount of dark matter that I get. Okay, so basically, if I'm drawing these different curves, those correspond to increasing sigma v.
Katelin,
Okay, because the more I increase, oh yeah.
Sign, unmute and ask your question, please.
Yeah, so I had a confusion in the previous case where the dark matter is relativistic. So here you were trying to see where the dark matter got decoupled, and from that you are trying to constrain the mass of the dark matter, right? But the time that dark matter got decoupled will depend on the interaction rate of the dark matter, and it will in turn depend on the velocity distribution, right? Because this NV average.
Yeah, good. So if n sigma v is sufficiently weak, then you're right. It will depend. But I guess maybe let me finish drawing this case over here, because so over here we have this is basically case B. So maybe let me label it. This is case B is over here. Let me choose a different color. Let me choose, I don't know, purple. Purple's a good color. This up here would correspond to case A. Okay, so basically in this line up here, you decouple while relativistic, and that means that you never ride this Boltzmann curve down. So you're always just constant. And so once you get to the point where so again, this is, moving down over here corresponds to increasing sigma v. At some point, if you lower sigma v, right, that means you're moving up in this direction, right? At some point you saturate and you say, okay, I've lowered sigma v now to the point where this decoupling is going to happen somewhere over on this shelf over here. It doesn't matter if decoupling happens here or if decoupling happens here, if it happens here, regardless of where along this part of the curve decoupling happens, you're still going to always end up with this density over here. So you're right, it does freeze out when it's relativistic does depend on the interaction rate, but because you're in this regime, the density that you get in the final state does not depend on the interaction rate. So that's a very good question. I feel like maybe that, hopefully that helps reinforce what I'm saying.
Okay, thanks. Yeah.
But yeah, so again, the intuition, intuition over here is that when you increase sigma v, so over here we're in, maybe let me also label. So let me scroll back up just to remind myself what are the two regimes. So in regime 2, that's when you follow the equilibrium distribution. So this is regime 2 over here, and this is regime 1 over here on this side of the plot. So when you increase sigma v, you stay in regime 2 for longer, right? So freeze out happens later, which means you ride this curve down further. So you ride further down this Boltzmann suppression. And because it's exponential suppression, you're then exponentially sensitive. The amount of dark matter that you get is exponentially sensitive to exactly where along this curve you actually decouple. Okay, so bigger sigma v means you stay in equilibrium longer, which means you have less dark matter. It's a little bit counterintuitive, but that's how the behavior of this differential equation actually works. Okay, so like I said, the freeze out temperature, T freeze out, is roughly m dark matter over 20. And that's correct up to log factors. I guess log corrections. So it doesn't really depend on the particle physics. And that's just coming from the relic abundance. So that's because of relic abundance. We observe. Okay, actually, I'm going to leave this as an exercise. If anyone wants to show that, that's a really good exercise. Okay. Okay, so great. So now this, so yeah, like I said, this is true. So now we want to know what value of sigma v in regime B is going to give us the observed amount of dark matter. Okay. And, throughout this lecture, I've been really loving to use estimation. So we're going to do that again. So let's try to estimate. So we're not going to try to solve, like I said, this is a Riccati differential equation. We're not going to try to solve this in detail because we just can't do it analytically. We would have to throw this on a computer if we wanted to get a really precise answer. We're just going to try to estimate it right now analytically. Okay. To do that, we're going to note that at matter radiation equality, so when rho matter is equal to rho radiation, then that means that, again, we're requiring that dark matter be non-relativistic at sort of these epochs. So that means that that rho radiation, or excuse me, rho matter is roughly given by m dark matter times n dark matter, which is a function of T. And so we're going to evaluate that at T of matter radiation equality. I'm going to ignore the contribution of baryons because they're a subdominant component. And so I'm going to say that the rho of matter is roughly equal to rho of dark matter. And so then at matter radiation equality, this quantity over here is proportional to T matter radiation equality to the fourth. Okay, this is just rho matter, and this is rho radiation. Okay. So what that means is that if I incorporate information about saying, okay, well, n dark matter at some t is the equilibrium density at freeze out times t over t freeze out cubed. If I use that fact and I plug that in, if I plug that into here, so it's a fact that we just established maybe a couple pages ago or so, then what that means is that the equilibrium density at freeze out has to be proportional to t of matter radiation equality times t freeze out cubed over the dark matter mass, over m dark matter. Okay, so that's one fact that's going to help us. I'm going to highlight it in orange. It's one helpful fact. Second fact that's going to help us is that we also know that at t freeze out, by the definition of what freeze out is, we know that n equilibrium at freeze out times sigma v is roughly equal to the Hubble parameter. And freeze out is generally happening during a radiation dominated epoch. Okay, so during a radiation dominated epoch, the Hubble parameter scales like t squared over m Planck. And we're evaluating this at freeze out. So this temperature is the freeze out temperature. Okay, so that's another fact that is helpful. Whoops. And if we combine these two facts, so if we combine these, of information, we solve for n sigma v, or I guess just in this case, sigma v. And we find that sigma v has to be proportional to m dark matter over t freeze out times 1 over the Planck mass times the temperature of matter radiation equality. Okay. So I showed you above, and I didn't prove it, but I left it as an exercise if you're interested, to show that the freeze out temperature, freeze out temperature is roughly the dark matter mass over 20 to give you the right relic abundance up to log corrections. So I'm just going to set this equal. This is just equal to 20. And actually, these things over here, these are known scales in physics, right? So in some sense, we're kind of taking a geometric average of the Planck mass with the temperature of matter radiation equality. Hugely different by so many orders of magnitude. Okay, when we plug in these numbers, what we find is that this has to be approximately 10 to the minus 26 centimeter cubed per second. Okay. So actually that's an important number. I'm going to highlight that. So that's the estimate. This actually agrees with solving the full Boltzmann equation numerically up to a factor of 2. So I love estimation. That's really powerful. So we didn't have to do any numerics. We just got to be a bit lazy, and we get something that's correct within a factor of 2. Okay. And now is where it gets pretty interesting. So now that we have this number, this is now going to get pretty interesting. We know that from dimensional analysis, sigma v has units of mass to the minus 2. Okay, so if sigma v doesn't depend on the velocity, which is called S wave. So if it's an S wave cross section, then by dimensional analysis, we know that sigma v has to scale like 1 over a mass squared. And what's what's the relevant mass in this problem? What's the only real mass that we've been dealing with in this problem? It's the dark matter mass. Now, I'm also going to correct this because by a dimensionless factor, because I know some particle physics, I'm going to correct this by a factor of alpha squared. Okay, that's just coming from the fact that I know that for some, tree level process, that's going to be how my process is going to have to scale with the coupling of whatever theory I'm dealing with. Okay, so just used basically dimensional analysis plus my, I'm only using a very, very minimal knowledge of particle physics here. So I'm trying to keep it fairly light on the field theory, but this is just a coupling of my theory. Okay, so let's maybe just, just for fun, stick in some scales that we know about. So for example, in electroweak theory, we know that alpha is on the order of 10 to the minus 2. And so to get sigma v of order 10 to the minus 26 centimeter cubed per second, then that implies that a mass, the dark matter mass, has to be on the order of 100 GeV. Okay, so electroweak scale coupling, and then you stick it into this cross section, which, recall, this cross section is up here. It came from this funny geometric mean of the Planck mass and the temperature of matter radiation equality. And so somehow when you put in this coupling and you have this geometric mean over here, and okay, yeah, whatever, you have some factor of 20, whatever, that's nothing compared to, the ratio of the Planck mass and to matter radiation equality temperature. Okay, when you stick in all of these scales, out pops this other scale that we know about. This is the weak scale. This is the weak scale. Okay, and so the fact that you have this really big coincidence, you might even call it numerology. You have this really big coincidence between, this geometric mean of Planck mass and temperature of matter radiation equality. Again, two numbers that are off by so many orders of magnitude. And you just put in some thermal physics and out pops the weak scale. That's a huge coincidence. Okay, and so that's actually often called, that's called the WIMP miracle. And here WIMP is weakly interacting massive particle. And here weakly, I mean in the sense of like electroweak. I don't just mean like feeble or not strong. I mean specifically in regards to the weak scale of the standard model. Okay, so this is a really huge coincidence. This is the WIMP miracle. And to my mind, this is actually one of the biggest reasons why WIMPs came to be one of the dominant paradigms on the dark matter scene. Yeah, I see there's a question, so go ahead.
Deep, unmute and ask the question.
So in this calculation, where did you use the correct relic density of the dark matter?
That basically came in, where was it? That came into knowing the temperature of matter radiation equality. So the abundance of dark matter comes in here.
So that would be scaled in our present universe to be the observed density. So
in the present day, yes. So yeah, all of these
doing
things.
The calculation in the matter radiation equality epoch, not in the present epoch.
Yep. So we can take the present day observed dark matter density and scale it back arbitrarily.
Okay. Okay. Thank you.
Yep. It also kind of comes in a little bit in this in determining this freeze out temperature. So that the present day abundance of dark matter gives me this factor of 20 here, but this is really peanuts compared to what's happening over here in this geometric average. So yeah, if you had maybe a difference in the amount of dark matter by a factor of 100, maybe this would change to be 30. So it's not very sensitive. So this is only logarithmically sensitive to various things in the problem. So it's really T of matter radiation equality. Yeah. Okay. Other questions? I mean, this is kind of a good place to pause, because this is kind of like a drum roll moment. This is the WIMP miracle. This is really one of the reasons why, to this point, we've spent however many millions of dollars that we've spent on trying to look for WIMPs. So this is a huge deal. Any more questions about that?
Are there any questions?
If not, I'll keep going. But oh yes, good.
Farman?
Farman.
Yeah.
Just one naive question about this, calling this a miracle, because you put in this coupling, electroweak coupling in the problem. So out pops the electroweak scale. So, so I was thinking whether, I mean, why is this so miraculous in that sense?
So you're saying, oh, didn't you cheat because you put in this electroweak coupling over here? So you already were putting in information about the electroweak scale. It didn't have to be that way, I guess. So if I had, for example, put in a slightly different coupling here, like if I had put in alpha of 10 to the minus 4, then this mass would have changed by orders of magnitude as well. Or conversely, actually kind of going back to the previous question, if the abundance of dark matter was different, then if I had plugged in this amount or this coupling, I would not have gotten this weak scale mass. I would have gotten some complete different mass. So in that sense, it's a miracle. Yeah.
Right.
So yeah, there's no reason why these two facts are linked a priori. These are only linked to each other through what's happening up here. Okay. Good. Yeah, I'm just pausing because this is a really important point. This is like a paradigm that came to dominate what kind of dark matter candidates we look for a couple of decades. Another reason I should mention is that WIMPs. Oops.
I noticed that Robert seems to have had a question/comment sometime back. Robert, would you wish to? I seem to have overlooked that. Robert, would you wish to ask that now or comment about it now?
No, I was just pointing out earlier that in the equilibrium distribution, the temperature depends on time.
Absolutely, yes, absolutely. So in this plot over here, right, absolutely. This temperature here is not fixed, so that's why this equilibrium behavior is like this. Yeah.
Thank you.
Good. So, okay, so this is the WIMP miracle. Oh, okay, more questions. Good. More questions about the WIMP miracle.
Rajesh,
Yeah, Rajesh.
proceed. Rajesh, go ahead.
Rajesh is still muted.
Rajesh, unmute and speak. Rajesh, you should be able to unmute and speak. Yeah, go ahead. Go ahead, Rajesh. Okay, he's
okay. Looks like, yeah. Why don't you type your question in the chat? I'm going to keep going, but I'll be happy to come back to your question towards the end. Okay. Okay. So yeah, WIMPs. So this is a miracle, huge coincidence. WIMPs are also generically expected in supersymmetric extensions of the standard model. So SUSY, which solves the hierarchy problem. So in addition to having this really nice, kind of nice coincidence here, we also are very easily able to incorporate this thermal history that we talked about today. We can incorporate that into supersymmetric theories very easily. So that's another really nice, nice kind of quality. Okay, so as far as the masses where this actually makes sense, so if we have some leeway, so with some leeway to vary alpha, so maybe, you know, all of the twiddles that I wrote down were just, you know, just naively putting in factors of alpha, but, you know, maybe in, you know, maybe in my favorite theory, there are some additional factors of 8 pi floating around, or maybe there's some additional factors that can change this sigma v. So naively, if I do that, then the maximum alpha is going to be of order unity. And here, this is an effective alpha. Okay, and that's the maximum for perturbativity. Okay, and so then if I plug in back into this requirement of having this cross section, that corresponds to a dark matter mass of around 1 TeV. So this is sometimes called a unitarity bound. It just says that in order to give you the amount of dark matter that we see, if we have sigma v that scales like this, and if we want to have the right cross section, then if we set alpha equals to 1, then the dark matter mass is 100. Oh, sorry, did I write 1 TeV? That was meant to be 100 TeV. Sorry if that was confusing to anyone. Okay, so it's 100 TeV unitarity bound. Okay, so WIMPs generically have to be lighter than 100 TeV. Okay, so MWIMP has to be less than around 100 TeV. At the same time, as we saw yesterday, we also need to satisfy all of the early universe observables that we know about, for example, BBN. So if the dark matter mass is around 1 MeV, then freeze out is happening right around the time of BBN. Then T freeze out is roughly T BBN. Okay, and as we saw yesterday, that's bad. So this is ruled out. Basically because you would mess up the Hubble parameter at TBBN. And so you would mess up the elements. Okay. So thermal freeze out, oops. So for that reason, thermal freeze out, which is this more generic mechanism that we talked about. So I would say this kind of situation over here, this is what I would call thermal freeze out. That is sort of restricted, to be between 1 MeV and 100 TeV. Okay. So that provides like a nice concrete window for us to look for dark matter. Okay, so now I'm actually going to switch back to my slides, okay, to show you a little bit of, you know, just to talk about the status, the observational status of searching for these candidates. So let me share my screen again.
So I noticed that Rajesh has the question in the chat. Can I read it out for you?
Yeah, go ahead and ask. Whoever is able to ask can ask.
Yeah. Sigma V comparable to 10 power minus 26 for freeze out. Is it independent of mass of dark matter? It's very weakly dependent. Actually, I have a plot of that I'm about to show.
It's very, very weakly dependent on the mass of the dark matter. The only real leading dependence that it has is just depending on when you freeze out, which again depends on the mass of dark matter because the freeze out temperature is proportional to the dark matter mass. When you freeze out determines what G star is in the standard model. So how many degrees of freedom are there in the standard model? And so through subsequent particles leaving the standard model bath and heating up the remaining species in the bath, that can change the story by some small order unity corrections. So that's the leading dependence. I'll show that in a moment, actually more quantitatively, but we ignored that for this estimate. Good. Other questions?
There's one more.
Oh, okay, I see there's another raised hand.
Cyan, go ahead.
Yeah, so I think yesterday, so in the plot of the mass constraint, like the plot that you showed yesterday, also in the first part of today. So there you said something about the relaxation of the constraints if there is some fractional dependence. I think that may be some. I'm not very clear about that statement. Can you just elaborate on that in the?
Sure thing. Yeah. So I'll just be brief because it's not so related to what I wanted to talk about for the rest of today. But on the two end caps of this mass range, the constraints that we set on these end caps depended on having all of the dark matter be one thing. So for example, on the low mass end, if the dark matter is bosons, let's say, then we said, okay, you can't have things below this mass because you're going to wash out structure because of the uncertainty principle. But if that dark matter is a subcomponent, like let's say you have a mix of WIMPs and 10 to the minus 23 EV bosons, that's actually totally fine because even if you wash out structure from the 10 to the minus 23 EV bosons, you still make some structure from the WIMPs. Okay, so there's some trade-off. Okay. So there's another hand, Dibyendu.
Yes. Dibyendu, unmute and speak, please.
Hello.
Yeah, go ahead.
Hi.
Yeah. So hi. So I just wanted to know that from the already available cosmological data, is it possible to constrain the epoch of dark matter formation? Irrespective of its production mechanism. How late it can be formed? Is it possible to constrain that?
Good question. So I would say at the latest by BBN. Yeah.
Okay.
Yeah, basically, because if you're trying to make this dark matter sometime after BBN, you need entropy for that from somewhere. So you might mess up various temperature ratios. And we know what it is at BBN. We know what it is at the CMB. So you have maybe some freedom to play with these temperature ratios, but not a ton of freedom.
Okay. So whatever the mechanism is, it have to be produced before BBN.
Yeah.
Okay. Thank you.
Sarush?
Hello.
Hi.
Yes, can you? Yeah. So hi. So I just wanted to know about the lower bound on the WIMP you just told. So isn't this Leeuwenberg bound more stronger? It's around 1 GeV, I think.
It is stronger. Yeah, I was going to come to that. I think we're running low on time, so I might have to come to that for the next lecture, but I was going to get to that next. So hold your question.
Okay.
Yeah.
Okay. Thank you.
Good.
Okay. Sure.
Robert?
Yes, this is in response to the way you answered the previous question. So if you have non-thermally produced dark matter, then the bound on the temperature doesn't apply. Is that right?
Yes, I agree with that. Then it becomes you still need to have dark matter by redshift 10 to the 7, based on what we talked about yesterday. So yeah, you're right. You can relax it, but not by a ton. Because yeah, the redshift of BBN is what, like 10 to the 9. So you can go from redshift 10 to the 9 to redshift 10 to the 7, but you don't have a ton of leeway.
Okay, thanks.
Yeah. Good point. Good point. Good. All right. So really quickly, in the last couple of minutes, I just wanted to talk about the status of WIMPs. In particular, I don't really have a horse in this race. I don't really think about WIMPs, but they are the classic dark matter candidate. And, you know, I think every generation, throughout the ages, every new generation has, some iconoclastic tendencies, right, to want to tear down what came before. And I think that's perfectly natural. But I think in the case of WIMPs, there's really no need to tear it down. You often hear statements these days, people saying, oh, WIMPs are dead. And that's really not the case. So I really want to just, in the last couple of minutes, talk about why I think WIMPs are still a good dark matter candidate to search for, even if I'm not personally doing that. Okay, so in this plot, this is really just a review of what I just said. So here, this is the thermal history. On the y-axis, I have the co-moving density. We see that when at early times when the particles are in equilibrium, so temperature increases to the left on this plot, which is a little confusing. So early times, high temperatures is on the left. We follow this Boltzmann suppression until we decouple, until we freeze out. At that point, the density becomes constant, and a weak scale cross section and weak scale mass gives you the observed density of dark matter, which is kind of a miracle. So this is a really predictive theory. Okay, so in my mind, the most direct way of probing this, sorry, it has these nice properties, but I don't want to talk about that right now because we're running low on time. But in my mind, the most direct way of probing this is through indirect detection, which is kind of a misnomer in that sense. What indirect detection is doing, or the sense in which it's indirect detection, is that what you're doing is you're saying, well, okay, suppose I'm living in a galaxy and I have some clump of dark matter over here, and I want to look for signatures of dark matter annihilating or decaying. So I want to look for those signatures, for example, with my very nice X-ray space telescope or gamma ray space telescope, and I want to look for those byproducts. And in doing that, one thing I'll note is that you're actually probing the same process where you're looking for those annihilation products as the process that was responsible in the early universe for determining the relic abundance, right? So you have chi goes to standard model. In the early universe, you also have it in your indirect detection. And so we're looking for these standard model byproducts. And like I said, it's really predictive. You have this known sort of sigma V that you're expecting to see based off of the early universe side of things, right? And so that's what that horizontal-ish dashed line is doing. A few minutes ago, someone asked, is the sigma V independent of the dark matter mass? And you can see that to good approximation, yes, it is roughly independent to within order unity factors. That bump right around, maybe a few GeV comes from, I believe it's the QCD phase transition. Okay, so you have this window here, that's this dashed line, and the low mass end is actually excluded by searches for visible particles in the final state in this plot. So if you have chi goes to standard model, if those standard model particles are going to have some, cascade or some sort of shower where they're going to go into some particle that's visible, like photons, then in that case, we would have seen them already. We would have seen them by now. In this case, the visibles include things like looking at dwarf galaxies with the Fermi Gamma Ray Space Telescope, as well as the CMB. So if you have too much of this process happening, you have chi goes to standard model, you're injecting energy into the plasma, and that can actually affect and mess up the onset of recombination because you're injecting too much energy, and so you keep things ionized for longer. So a combination of those things actually rules out the low mass end of this parameter space. So that's great. So actually we know from observation, so without even having to do any more theory, we know from observation that WIMPs below 10 GeV are not really viable, okay? We also know on the high mass end, we just made some theoretical arguments. We have this unitarity bound, which says that you can't really have WIMPs heavier than 100 TeV. And so we have this very finite range of masses where we can look for WIMPs and where they're still viable. The prospects for closing this window in the near future with indirect detection are not fantastic, but maybe if we're very futuristic, we can close this window with indirect detection in the future. Although one kind of caveat is that we're always subject to astrophysical uncertainties in these cases. So that's kind of a thorny issue. At the same time, though, we have this very active program on the direct detection side, where we look for dark matter coming into our lab and scattering off of some experimental apparatus and giving us something that we can actually look for in terms of some sort of a recoil. Okay, this is an out-of-date plot from the SNOMAS 2013 report, but I like it because it just shows a lot of different experiments all on the same plot. So it's really showing that a ton of time and energy has been invested into looking for WIMPs. So that's how seriously the community is still taking these candidates. And this was an old plot, so many of the lines in this plot, which are dashed or dotted, at the time, those were projections or forecasts, but now those experiments have realized their full sensitivity. So a lot of the parameter space on the upper region of this plot is now ruled out. And so because we haven't found dark matter through this way, that's, I think, the genesis or the origin of a lot of the pessimism that I hear. But one thing that's really super important to note is that the process that you're probing here is scattering. It's not annihilation, okay? So the way that the dark matter comes in and scatters off of your apparatus in your lab, the way that you equate that to early universe annihilation is heavily, heavily model dependent, okay? So you actually can't really make, based off of this plot alone, you can't really make any robust statements about whether or not WIMPs are the right dark matter candidate. In fact, it's entirely conceivable that WIMPs are the dark matter and that they just live somewhere below this orange line on the bottom of the plot. This is the so-called neutrino floor. And that's the point where neutrinos from the sun are going to actually swamp these dark matter detectors and make it really difficult to see dark matter. It's entirely conceivable that WIMPs live below the neutrino floor, okay, and that there's still WIMPs and they still explain the abundance of the dark matter of the universe. So I think WIMPs are very much still alive. Just because we haven't found them yet doesn't mean that they're ruled out. There's a lot of space still left. At the same time, though, I do not work on WIMPs. I do have that little iconoclastic streak. So I really think that there's a lot of motivations to go beyond the WIMP paradigm. So we have the WIMP, that's a great candidate, but I think there are fantastic reasons to go beyond it. And that's what we'll talk about tomorrow. So thanks again for all the questions, and be happy to answer any more for now, but I think we're at a good stopping point. So we'll pick this up again tomorrow.
Thank you, Katelin. Questions for Katelin? Are there any questions, students? There is one hand raised. Sign, go ahead, unmute and speak.
Yeah, sorry. I'm sorry if I didn't understand this. So in the second regime B, where the dark matter mass is greater than the freeze out temperature, I didn't understand how did you got actually the freeze out temperature is mass divided by 20. Can you repeat that point?
I actually didn't show it. I left it as an exercise for you guys. But I can give you a hint. So the way that you actually show it is by saying, okay, well, I know what the density of dark matter is today. So I know that at late times, I can just scale back what the density of dark matter is today up to early times, just given how it's redshifting. Okay, and then I can actually say, okay, I'm going to do that all the way up until the point where freeze out occurs. Okay, and then I say, okay, well, freeze out's occurring. So I know that, my number density that was flat at late times has to intersect this exponential curve at some point. And you find that intersection, and you find that intersection occurs very close to a temperature of the mass divided by 20. That's how you go about it. But it's not easy to do in a lecture format because you need to solve that numerically or graphically. And I didn't want to do that. So I leave that as an exercise to you.
So in a way, we know the history of the temperature, how the temperature of that dark matter changes, and we know the history of the mass, how the mass changes. The density changes, and we try to make a relation between those two. Is that correct?
Exactly. Exactly. So you saw that Boltzmann curve looks as a function of temperature if I supply the mass. So once I supply the mass, I know how that looks as a function of temperature. If I also supply not only the mass, but the density of dark matter, I also know what the density of the dark matter is. And I know how to scale that after freeze out in time, because it's just redshifting like matter. So that's how you solve it. Yeah.
Okay, thanks. And one more thing, yesterday you showed us some animation of some clash of two cluster where the dark matter didn't interact and the baryonic matter interacted and it slowed down. So can you go to that plot? So I didn't understand how we are seeing the dark matter kind of thing. Like,
yeah, let me, that was in my lecture from yesterday. So let me pull up the PowerPoint for that, just so that everyone can, just because I know people don't have perfect recall, just want to make sure everyone's clear on what we're talking about. Okay, so let me share my screen again. It's this one, I think. Share. Okay. Yes. Good. So this is the picture that you're referring to. So right. So this is a composite image. We're seeing the normal matter in X-rays. So with Chandra X-ray Space Telescope, we can see the normal matter. The reason why we can see it is that it's extremely hot. So I guess this is the animation you were probably referring to. This is the merger of these two regions, and the pink stuff represents the ordinary matter. And as you pointed out, this pink stuff gets slowed down as this merger is happening. The reason why is because regular matter has collisional drag. It's able to, you're able to transfer energy and momentum on a particle by particle level through scattering. And so through this exchange of energy and momentum on a microphysical level, you're taking, so maybe let me play the movie again. You're taking a huge amount of kinetic energy, and through this process, you're taking that bulk kinetic energy and you're converting it into thermal energy. So you're making this stuff really, really hot. Maybe another example, so this is called the bullet cluster because the littler cluster is moving through the bigger one like a bullet. I think that's actually a really good analogy. So if you ever, fire a gun, which, I wouldn't necessarily advise, but if you do, then after you fire it, you feel the barrel of the gun is actually hot. And that's partly due to the fact that as the bullet travels down the barrel, there's a lot of friction, and so it heats up. Okay, so this regular matter gets heated up to the extent that we're able to see thermal emission in X-rays. So it's got a thermal spectrum. So that's where the regular matter is. And we know it's regular matter because it experiences collisional drag, and it heats itself up because of friction, which is ultimately the origin of friction is Coulomb interactions, right? So that's where the regular matter is. The blue stuff, on the other hand, is seen using gravitational lensing. Okay, that's this technique where we're using the fact that in this image, we have all these background galaxies. So if there's some concentration of matter in the foreground, you're going to distort the background images in a correlated way, and you can infer where the foreground mass of the lens actually is. And the really important point about this image is that the two regions they're not sitting on top of each other. The bulk of the mass of the system does not correspond to where the baryons are. So whatever is in the system, the bulk of its mass is not baryonic, and it's not behaving like baryons in the sense that it's not collisional. It's not being slowed down as this merger is happening. Okay.
Yeah. Okay.
Hopefully
so
that clarifies.
So the lensing is the proof of seeing the dark matter sector of that cluster, right? And the lensing of the background galaxies, that's what you're talking about.
Exactly. So it's the lensing, and in combination with the fact that the regular matter and the lensing inferred matter, the fact that they don't overlap, that's how we can infer that there's dark matter in this picture.
Yeah. Okay. Yeah. Thanks a lot.
Thanks, Hein. There is a question from Rajesh. Go ahead, Rajesh.
Can you hear me, sir?
Yes, we can hear you.
Ma'am, where you plot the cross-section versus dark matter mass, you have given a unitary bound. Can you tell me why the dark cross-section is not greater than unitary bound?
Okay, let me go back to my PowerPoint of today. So, okay. You're talking about this purple unitarity bound?
Yes, but it is not exceed the unitary bound. Why the reason?
Sorry, can you repeat that?
I mean,
why shouldn't it exceed the unitary bound?
Good. Okay, so the reason why you can't exceed the unitarity bound is because that would require a non-perturbative value of the coupling.
Okay, thank you.
So yeah, at that point, it doesn't even really make sense to like necessarily talk about like individual particle scattering. It's going to be some, much more complicated, horrible many-body problem when things become strongly coupled.
Thanks, Rajesh. There's one more question. Shashwat, go ahead.
Hi, so my question is regarding warm dark matter as a potential candidate. I was just wondering whether, so from your lecture, it seemed like warm dark matter is basically ruled out. Am I understanding that correctly? Or is there still a chance that a fraction of the dark matter could be warm dark matter?
Yeah, as soon as you start talking about fractional components of dark matter, then it's like the Wild West, like anything goes. For warm dark matter to be 100% of the dark matter, in its most sort of classical formulation that I presented today, I think it's very unlikely for that to be the dark matter, just because you have to explain where do you get all these degrees of freedom from. So that's really not explained in that context. People still talk about warm dark matter though, all the time. It's not that they're having some sort of collective hallucination. It's because warm dark matter at this point is a really well-studied model for particles free streaming in the early universe. So you can have other situations beyond just warm dark matter. So beyond what I showed, where the dark matter is free streaming in the early universe. And warm dark matter is an example, a toy example of that. So because it's a toy example and it's so well studied, people still talk about constraining it, even if it's not the literal theory that they're like literally interested in constraining. And the reason why is because you can take limits on warm dark matter and basically port them over to other theories or other thermal histories that have this free streaming property. So in fact, that's something that I myself have done in my quest to constrain dark matter. So I guess my answer to your question is mixed. It's like warm dark matter is not like literally a good theory, but the thermal history that it maps onto is still a good theory, up to the level at which it's been constrained.
Thank you, Katelin. I don't see any questions now. Any hands raised? Let me check the chat. There are none for now, Katelin. So
Okay.
we can stop here for today.
Great.
Okay. Thank you. Thank you very much, Katelin. We'll see you all tomorrow.
See you all tomorrow.